Dear students, let's proceed with our lectures on the topic of usage of Laplace transformation for determination of transient processes in circuits with linear parameters. And it is last part of this set of lectures, and there are some remarks on the usage of operational method or method of Laplace transformation application. First, if we have I would like to remind you that we present third solution function as a ratio of numerator function phi1 from P and denominator function phi2 from P, which we present as polynomial functions. And these remarks tells us that if phi2 from P is denominator of third Laplace image of Laplace image of third function, and if it has root P equal to 0, so third function, it means function of time, will have constant first component. Why? I have shown you in previous lecture example of usage of Laplace transformation for transaction from Laplace image to function of time. We've got Laplace image of current and we transact to function of time to original of this Laplace image, and we have had one root, it was P1 equal to 0, and you see when we substitute in formula of decomposition theorem this root in exponential function, we will get in the degree 0 multiplied by t in 0 degree, so we will have constant item, constant summand, which will not depend on time, and so it refers to DC component. So if we have such 0, one of our roots is 0, therefore third function image of original of third function has constant first component. Second remark, if phi2 from P, if denominator has roots complex and conjugate P1 2 equal to plus minus j omega, j its imaginary unit equal to square root from minus 1, therefore third function has sinusoidal first component. I will show you later on why it is such a way. And if we have two complex conjugate roots, and as a rule it is such a situation, and if there are such two complex conjugate root among denominator roots phi2 from P equal to 0, I remind you that phi2 is just denominator of the obtained function of P, of Laplace image of the third function. So if we have such two conjugate roots in denominator, therefore we can function of time phi from t will be also complex and conjugate, corresponding this coefficient aak, with the help of which we present this coefficient, will be also complex and conjugate. And when we sum up two conjugate complex number, their imaginary part will be reduced and their real parts will be doubled. You see, because we have, for instance, a plus j omega plus a minus j omega. A plus j omega, it will be 1, a plus it will be, for instance, first root, and a minus j omega will be conjugate to this first root number. And when we sum up two conjugate number, we do know that conjugate complex number differ only by sign of their imaginary part. So when we sum them up, the imaginary part will be cancelled and their real parts will be doubled. So there is an example of usage of this this state. For instance, we can present phi2 from P, denominator of obtained image Laplace of the third function, in such a way P multiplied by P power 2 plus 2 delta P plus omega 0 power 2. And let's consider case when delta it's 2 over r over 2l less than omega 0. Omega 0 is 1 over square root from LC. And therefore we have first root P1 here equal to 0, and second and third root will be from here, from solution of this when we equate this expression in brackets to 0, we will have roots of this expression as minus delta plus minus j omega c, where omega c is square root from omega 0 power 2 minus delta power 2. It was all explained before in previous lectures, but it is obvious from solution of this second order equation. See? So let's determine original function of time for such a function, when we have such denominator of Laplace image. We have here, let's consider that numerator is phi1 from P, so it will be phi1 from the, using decomposition theorem. We should sum up summands. Each of summand we will get by substitution each of roots in such an equation. So it will be phi from t will be equal to phi1 from p1 equal to 0, phi1 from 0 over phi2 prime from 0 multiplied by integral 0 multiplied by t, because p1 equal to 0. Okay, it will be, you see, it will be just as it is 1 unit. We will have from here we will have phi1 from 0 over phi2 prime from 0. This item will be written in such a way. Then we should twice expression a substitution of the first of, no, here it is second root, it will be minus delta plus j omega c, substitution in decomposition theorem formula, okay, and we should take real part of expression in brackets and twice it, okay, 2 and real part, okay. Just to simplify this calculation, if we substitute first this second root minus delta plus j omega c, and then third root minus delta minus j omega c, we will have the same result. So we just simplify our calculations, and it will be first summed, as I have told you, this way, yes, and second it will be let's present this it will be complex number, because we substitute instead of p2 complex root, so it will be complex number and may be presented in polar form as product of module of this complex number multiplied by integral j phase of this complex number. The same refers to denominator. We can take derivative from this expression, then substitute here this complex root, and also present it in polynomial form as product of module. We will not calculate now this module, just present in a common form module n multiplied by integral j bay, where bay beta, sorry, it's phase of this expression, okay? And it should be multiplied by e to the degree, and now we should substitute this root minus delta plus j omega c multiplied by t, okay? Take real part. What it will be? It will be, you see, it will be 2 m over n, because it is real numbers. They can be put before brackets. Yes, it is just a coefficient. Then e to the minus delta t may be put before brackets also, because it is also real number like a coefficient. And then we should take real part from e to the j omega c t, and real part of such an expression equal to, by Euler's theorem, equal to cosine of omega c t, yes, and we sum up here plus alpha and minus beta. We can write down this ratio is j alpha over e to the j beta as e to the j alpha minus beta, and we can write down that it will be e into the j alpha minus beta plus omega ct. And when we take real part of this exponential function, complex exponential function, we will have just cosine of this argument omega ct here plus alpha and minus beta. Minus beta because beta is in denominator, alpha is in numerator. So we can rewrite it using not cosine function but sine function by adding 90 degrees to argument of this cosine, because we are used to write it through sinus function, not cosine. So we can write down that this summand can be write down as a forced component, because it is, you see, it is constant, and it is obvious that it is not natural component, and this component will be natural because we have here coefficient e to the minus delta t, and this coefficient will tend to 0 when t tends to infinity. Sorry. So we can write it down as phi, this we can write down as phi maximum natural multiplied by this 2m over n multiplied by e to the degree minus delta t multiplied by sinus omega ct plus phi natural, where phi natural is alpha minus beta plus 90 degree. And we can see that this in such a case transient processes is oscillatory, because we have a natural component we changed in accordance with sinusoidal law, which diminish in time. And one more remark. I have told it earlier. The elements of operational method may be used to solution of the problem with the help of classical method. I have told you in the end of our lectures on the topic of classical method. And in such a case, we should write down operational impedance of the circuit after switching with respect to any pairs of terminals by writing of this expression of impedance and equated it to 0, and in such a way we can determine characteristic equations root, and in such a way we can write down solution for transient processes with the help of classical method. So students, dear students, it is the part concerned with transient processes solution with the help of Laplace transformation and classical method transformation is over, and in next lecture we will start with another part of our a course, and it will be with the case of distributed parameters of the circuit. Let's meet next lecture, and bye bye for now.